In this lesson, we are going to learn how to find areas between two curves. Let's consider the simplest case first. So suppose we want to find the area of the region bounded by two continuous curves, f of x and g of x, and the vertical lines x equals a and x equals b. We assume that f and g are continuous functions, and f of x is greater than or equal to g of x on the entire integral. So a definite integral finds the area under one curve. How do we find the area between two curves? So let's draw a picture. The x-axis, the y-axis. All right, so your curve f of x is greater than or equal to g of x. And to make it a little more complicated, let's actually have g be negative sometimes. And we have some vertical line x equals a, and some additional vertical line x equals b. And we want to find the area bounded by all these curves. And so back in Calculus 1, when you first did this, you said, okay, well, I can find the areas of boxes. So let me make a whole bunch of boxes. And let's find the area of each of those boxes. So note that each box will have width, what we're going to call approximately delta x, so change in x. Actually, each box will width exactly delta x. Now, the height of each box will be approximated by taking f of x minus g of x. And notice that this works even if g of x is negative. So like, for example, there, if the value of f of x was 5 and the value of g of x was negative 3, doing f minus g yields a result of 8, which is the actual height of that box. And so your area would be approximately equal to a sum from, say, I equals 1 to n of all the heights, f of x sub I minus g of x sub I, delta x. That idea of approximating things by breaking it up into chunks is a pretty important idea in this section, so it's good to get used to it. And if you take this to make the area exactly, you take the number of chunks and you limit that to infinity, so n goes to infinity. And then by definition, this becomes an integral from a to b of f of x minus g of x. And notice here that f of x is your upper curve, g of x is your lower curve. Something else to notice is that an integral really is a sum. That's why the integral symbol is S-shaped. So what this thing does is it sums up a bunch of heights with sort of infinitely small widths. So sort of you're summing up kind of like a bunch of lines, and the whole process of summing those things up makes it a two-dimensional object in the end. So, but the basic idea is you integrate between your two values and you do your upper curve minus your lower curve. Now, if the curves change, who's upper and lower, the process is a bit more complicated, and we'll discuss that in a later example. So find the area of the region enclosed by the parabolas y equals x squared and 2x minus x squared. So step one that you should always do is to graph your region. So y equals x squared is easy enough. That goes through 0, 0, 1, 1, 2, 4. Now graphing 2x minus x squared is a little bit more tricky, but what you can do is factor out an x and look for the x-intercepts by setting y to 0, and you get that x is 0 and 2. So that particular parabola crosses the x-axis there and there, and because we have a negative x squared, we know it's upside down. If you plug in 1, you're going to get out 1. It will look a little bit like this. So the region we're looking for is the area of that little bitty region right there. After you've graphed, find the points of intersection. So in this case, it's pretty obvious from the graph what they are. They are the points 0, 0, and 1, 1. In particular, x equals 0, x equals 1. If you did not have the graph, the way you would find that is by taking x squared equal to 2x minus x squared and solving it for x. All right, now you have all the information that you need to find the area. So the area will equal an integral. So in this case, our a is 0, our b is 1. The upper curve is the upside down parabola, so 2x minus x squared, minus the lower curve, which is x squared. And now we have a pretty easy function to antidifferentiate. So 2x minus 2x squared. So the antiderivative of 2x is x squared minus 2/3 x cubed from 0 to 1. So that will be 1 minus 2/3 or 1/3. So let's do another one. So find the area of the region enclosed by the curves y equals x plus 1 and negative x squared plus 4x plus 1. So the first one is a line, y-intercept 1, slope 1. The second function is a parabola, and I think the easiest way to graph it is to complete the square. It's my personal preference. So to do that, you take the negative out of the first two terms, write it as negative quantity, x squared minus 4x, and tack your plus 1 on the end. Now, the completing the square process, you add half of this number squared inside those parentheses, so that you will add 4. And what that's going to do is make this into negative the quantity x minus 2 squared. Now, you've actually added in a negative 4 because of the negative sign out in front. So to compensate, you add 4 on the end, so you've effectively added 0. So there's our equation for our parabola now. Now this will be an upside down parabola shifted right 2 and up 5. So its vertex is over 2, up 5. 1, 2, 1, 2, 3, 4, 5. And there's the rest of the parabola. Next point's down 1 over 1, then down 3 over 1. So what we're looking for is the area of this region. And as long as your picture is really accurate, you can see that the intersection points occur at x equals 0 and x equals 3. If you wanted to find those exactly, what you'll have to do is solve x plus 1 equals negative x squared plus 4x plus 1 if your graph isn't good enough to tell what they are. All right, now the area between these curves will be given as the integral from 0 to 3. Your upper curve is the parabola, negative x squared plus 4x plus 1, minus the lower curve, which is x plus 1. Make sure you put that in parentheses. And from there, it's pretty simple. Integral 0 to 3, negative x squared plus 3x. So that antidifferentiates to negative 1/3 x cubed plus 3 over 2x squared, evaluated from 0 to 3, or minus 27/3 plus 27 halves. That's the same thing as negative 9 plus 27 halves, or negative 18 halves plus 27 halves is 9 halves. Now let's again assume that f and g are continuous on some interval from a to b. And so in this case, what if it is the case that these two curves for f of x and g of x, what if sometimes f of x is bigger than g of x, but sometimes the opposite is true? Sometimes g of x is bigger than or equal to f of x. What if that happens? So in this case, let's draw a picture. So you have some curve y equals f of x, some other curve y equals g of x, and I said I want the area between this value and this value. And let's call that point where they intersect in the middle some point C. So the definition we had in the formula we had in the previous examples depended upon the fact that f of x was always bigger than g of x. So the only way to deal with this case, and it's tedious, is to break this into two pieces. The area will be found by first integrating from a to c, and in that case you'll do f of x minus g of x. That will get you this area. And then you add the integral from c to b, and because g of x is greater than f of x there, you do g of x minus f of x. And you'll get that area there. That's why graphing your function is so important, so you can see, do these curves intersect on the interval that I'm given, and do I have to break it into two different pieces? All right, let's do an example where this applies. Find the area between the curves sine x and cosine x between 0 and pi. All right, so both sine and cosine go through one cycle in 2 pi. So pi, 2 pi, here we have half pi and 3/2 pi. So sine begins at 0. By pi halves, it's up at 1. By pi, it's back down at 0. 3 pi over 2, negative 1. 2 pi, we're back to 0. So there's the graph of sine x. Now cosine x, cosine of 0 is 1. By pi halves, we're down at 0. By pi, we're at negative 1. 3 pi halves, we're at 0. 2 pi, we're back at 1. And we want to find the area between 0 and pi, so that's this part plus that part. That's the area that we're looking for. Now you need to figure out where these two curves intersect. So where does sine x equal cosine x? And looking at your unit circle, you should know that that occurs at pi over 4. It occurs in more places than that, but the place that we care about is the one that's between 0 and pi. So right there is pi quarters. So to find the area, I have to break this into two integrals. So my area will equal, first I integrate from 0 to pi quarters. And for that portion, the cosine curve is greater than the sine curve. So we'll do cosine x minus sine x dx. And then for the remainder of our interval, from pi quarters to pi, it's the opposite. The sine curve is above the cosine curve. All right, now antidifferentiate. The antiderivative of cosine is sine plus cosine, because cosine's derivative is negative sine, so it's from 0 to pi quarters. And then the antiderivative of sine is negative cosine, and then the antiderivative of negative cosine is negative sine. And then you do have to know values of your unit circle. So the first thing we're doing is plugging in pi quarters. At pi quarters, sine of pi quarters is root 2 over 2. Cosine of pi quarters is also root 2 over 2. Then you plug in 0. Sine of 0 is 0. Cosine of 0 is 1. All right, next we plug in pi to the next part. So negative 1 minus 0 minus negative root 2 over 2 minus root 2 over 2. If you're going to lose anything here, it's just keeping track of those negative signs is the trickiest thing. So root 2 over 2 plus root 2 over 2 is root 2. Then we'll have minus 1 plus 1 minus negative root 2, which gives us 2 root 2. So that area is 2 root 2. If you do not break this integral into two pieces, you are not going to get the correct result. So set up, but do not solve an expression that gives the area between the curves 8 minus x squared, y equals x squared, and the vertical lines x equals positive negative 3. So graph these curves. So 8 minus x squared is a parabola that's up 8. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. When you input 1, we get 7. When you input 2, we get 4. Okay, so approximately like this. Now y equals x squared. Well, that goes through the origin, and 1, 1, and also 2, 4. Notice that those intersection points are at x equals positive or negative 2. And I said vertical lines, negative 3 and 3, so those vertical lines, those are over here. So the area we're looking for is this little bit, that middle bit, and this part, all of that stuff. And notice that which curve is above changes at the points positive, negative 2. So technically you have to break this into 3 pieces, but you could use symmetry to make the computation easier. So we'll discuss the basic setup, and then we'll discuss the symmetry bit. So first of all, you have the integral from negative 3 to negative 2. So that's this portion right there. So for that portion, the x squared is the curve above, and the lower curve is the 8 minus x squared. Then for the middle portion, from negative 2 to 2, the 8 minus x squared curve is above, and the x squared curve is the lower curve. And then lastly, from the 2 to 3 portion, the x squared curve is above, and the 8 minus x squared curve is below. Now notice that this area is equal to that area due to symmetry. So a better way to express this would be to write twice the integral from 2 to 3 of 2x squared minus 8. It probably is easier to compute this integral using positive values than the other one using negative ones. And also notice that with the middle part, this area from negative 2 to 0 is equal to the area from 0 to 2. So what you can do instead there is do twice the integral from 0 to 2, 8 minus 2x squared. And that's the setup that you would use to solve this. If you have lots of patience and some extra time and you decide to solve this, you should get 92/3. Most of the work for these problems is in the setup. All right, now what if we have 2 curves that are described by continuous functions of y? So instead of being y equals, they are x equals. And you want to find the area between those. And we're just going to assume that f of y is bigger than or equal to g of y in this case. All right, what that will look like is this. So here's what we'll call my curve x equals f of y. And below it is the curve x equals g of y. And I care about the area between those curves from some lower value y equals c to some upper value y equals d. And you've got to think, okay, how would I find that area? So this is pretty similar to the other stuff we did. You just have to think about which curve is the upper curve. So think about the x-axis. The positive direction of the x-axis is that way to the right. So in this case, upper translates to rightmost. Lower translates to leftmost. So this is the larger x, that is the smaller x. So in general, the area will be found here by taking an integral from your lowest y to your highest y. So note, these are y values now, not x values. And we'll take f of y minus g of y. And where f of y is your curve on the right, g of y is your curve on the left. Okay, let's try one of those. So find the area enclosed by this line and this sideways parabola. So first, graphing the line, start at -1. Your slope is 1, so rise 1, run 1. All right, and graphing that parabola, I think it's going to be easiest to solve that for x. So 2x would equal y squared minus 6, and x equals 1/2 y squared minus 3. So I'm going to make a table because I'm just not 100% certain what points that thing goes through. Now instead of picking x and finding y, I'm going to pick y and find x. So if y is 0, x is -3. So back 3, up nothing. If y is, let's say 2, doesn't get a fraction that way. If y is 2, 2 squared is 4, half of 4 is 2, 2 minus 3 is -1. So back 1, up 2. If I'd plugged in -2, then x would also be -1. So we've got -1, -2, look at point of intersection right there. And another easy number to plug in would be y equals 4. So 4 squared is 16, half of 16 is 8, 8 minus 3 is 5. Got the point over 5, up 4. Oh look, it's that point. So if you graph very carefully, you will actually find your points of intersection. So that's the area we want to find. Now the first thing is figuring out your bounds, and the kicker with this method is these numbers you use have to be y numbers. So y equals, at that point, it's -2. At this upper point, the value of y is 4. And the other thing is that the curves must be written as functions of y. So for example, this first curve will have to be written as x equals y plus 1. And notice that that is actually also our rightmost curve. And our other curve has to be written like this, so minus the quantity 1/2 y squared minus 3. Now let's continue integrating by combining like terms. So you have the integral from -2 to 4, -1/2 y squared plus y plus 4. Anti-differentiate, and the antiderivative of -1/2 y squared is -1/6 y cubed. And the derivative of y is 1/2 y squared plus 4y. Evaluated from -2 to 4, which will give us -64/6 plus 16/2 plus 16 minus 8/6 plus 4/2 minus 8. So that's -32/3 plus 8 plus 16 minus 8/6 minus 2 plus 8. Now notice 8/6 is 4/3, so that's -36/3 plus 30. And -36/3 is the same thing as -12, which gives us 18. All right, let's do a little bit simpler one. So find the area between the curves x equals 1 minus y squared and x equals y squared minus 1. So for the first one, let's just make a table and plug in some numbers. X, y. So if I input y equals 0, it looks like that I get x equals 1. If I input y equals 1, it looks like I get out x equals 0. If I input y equals -1, I also get out x equals 0. And if I input 2 for y, I would get x equals -3. So back 3 up 2. And if I were to input -2, I would also get out -3 for x. So back 3 down 2. All right, now for the other curve, if I input 0 for y, I get -1. If I input 1 for y or -1 for y, in both cases I get 0. So there we go. And if I were to input, say, 2 for y or -2 for y, so in the case of 2, I get that x is 3. In the case of -2, I also get that x is 3. So I graph the point over 3 up 2 and over 3 down 2. So the area we're looking for is this little area in the middle, and the y values of our intersection points are -1 and 1. So the area is the integral from -1 to 1. Now the upper curve is this one. So that was the 1 minus y squared curve. And we're going to take away from that the lower curve, which is y squared minus 1. Now because of symmetry, we can say that's twice the integral from 0 to 1. And this will simplify to 2 minus 2y squared. So that's 2 times 2y minus 2/3 y cubed, evaluated from 0 to 1, or 2 times 2 minus 2/3, which is the same thing as 2 times 6/3 minus 2/3, which will give us 2 times 4/3, or 8/3. Now, lastly, let's do some applied problems. So this figure shows the velocity curves for two cars A and B that start side by side and then move along the same road. What does the area between these curves represent? So I think we're specifically talking about from 0 to 16. So the integral from 0 to 16, we'll just say that's a of t dt. That's the distance that car A travels. The distance from integral from 0 to 16 of B is the distance car B travels. So since the area underneath the A curve is greater, that means car A traveled farther than car B does. And so the integral from 0 to 16 of, we'll say, A of t minus B of t, this is how much more distance car A covered. Or you could say it's how far ahead car A is of car B. All right, another example. So if the birth rate of a population is given by this equation B of t, and the death rate is given by the second equation, find the area between these curves for 0 to 10, and then what does this area represent? Now, if you are to graph these curves, they're both exponentially increasing, but this one begins at time 0 at a higher value. So B of t, and also the rate of growth, is actually 2.4% versus this 1.8%. So curve B is always going to be above curve D. And so the area between these curves is going to be the integral from 0 to 10 of b of t minus d of t. So that's the integral from 0 to 10 of 2,200 e to the 0.024t minus 1460 e to the 0.018t. And now anti-differentiate, and we'll have 2,200 over 0.024 e to the 0.024t minus 1460 over 0.018 e to the 0.018t, evaluated from 0 to 10. And at this point in time, use a calculator, and this is approximately equal to 8,867.99, so that's about equal to 8,868. And so first let's think about what the units would be. So the b of t curve and the d of d curve, the units there for the y are people per year. So on this axis you have people per year. On this axis you have years. So the area's units are going to be people. And since you did births minus deaths, this tells you what the population increase. So this tells you the population increased by 8,868 people during this 10-year period. And that does assume that we don't have any kind of people coming in or going out, but just, I think in general, it's the amount the population increased by, or how many more new people there are. Now lastly, kind of a theoretical example. So find the value of c such that the area of the region bounded by x squared minus c squared, and c squared minus x squared is 576. So think very generally about what that curve is going to look like and what that curve is going to look like. So x squared minus c squared will be a parabola that has a y-intercept of negative c squared. It's actually going to cross the x-axis at plus or minus c. But roughly speaking, it'll look something like this. Now the other parabola will be an upside down parabola. Its y-intercept is at positive c squared, and it also has the same x-intercepts. And we're going to actually prove that that's true. We want to find what value of c makes that area 576. So first let's verify that the intersection points are positive, negative c. So set x squared minus c squared equal to c squared minus x squared. That gives us 2x squared equals 2c squared. X squared equals c squared, so x does equal plus or minus c. Now to find the area between them, you take the integral from, well, negative c to c. Your upper curve is c squared minus x squared. Your lower curve is x squared minus c squared. dx, that tells you x is your variable, and that needs to equal 576. So first of all, some symmetry. This is the same thing as twice the integral from 0 to c. And combine some like terms, we've got 2c squared minus 2x squared equals 576. And just to make things easier, let's divide by 2. So 576 divided by 2 is 288. Okay, and we could divide by 2 again, say factor out a 2 and then divide by it. We'd have the integral from 0 to c, c squared minus x squared, 288, I forgot my dx's, 288 divided by 2 is 144. All right, now here's the trickiest part. C squared is a constant. When you antidifferentiate that constant, its antiderivative is c squared x. kind of like the antiderivative of 4 is 4x. The antiderivative of x squared is 1/3 x cubed. And we're going to figure that out between 0 and c, and it has to equal 144. So when you plug in c, you're going to get c cubed minus 1/3 c cubed. Well, that's 2/3, because this is 3/3 c cubed. So this is 2/3 c cubed equals 144. So therefore, c cubed, well, you can do 144 divided by 2 and then multiply by 3. Anyhow, you're going to get 216. And c is the cube root of 216. So c equals 6. After years of giving that problem, the most common error that I see is here. Students want to say that the antiderivative of c squared is 1/3 c cubed, but this dx tells you that x is your variable and c is a constant. So you need to treat c like any other constant, even though it's a letter.